Based on the American Public Transportation Association's data, a total of 4.5 million people used 25 different rail systems in 2013. 97 million alone used the MTA Long Island Railroad system, which is the largest in the country. Along with these highly used long-distance passenger trains, people in metropolitan areas rely on the metro system to travel from place to place within the city. The largest metro system in the United States is in New York City, which averages 1.3 billion riders per year. It spans 230 miles around the city. In addition to New York City, the Washington, D.C. average weekly travel for their metro system is 602,000 people, which totals to 2.8 million over the course of a year. Metros are run off electricity supplied from the third rail on the track. Metro trains run on 800 volts, enough to propel a packed rush hour train at a speed of up to 70 miles per hour. The electricity can be from any number of sources, be it nuclear, hydro, coal, oil, wind, or sun. But often the most efficient source of electricity will be coal, even though it is very harmful to the environment. Most modern trains contain a diesel engine that powers an electric motor which turns the train's wheels. While the modern trains release less of a byproduct compared to older steam engines which ran directly off of coal, their emissions still harm the environment. Current trains are outdated and make travel slow with frequent stops and changing of engines and tracks. The coal which runs both the metro system and the above-ground rail system is harmful to the environment and only provides a short-term energy solution. It is only a matter of time before no more coal is available.
Metros today are sufficient enough to travel small distances, but there are better options for long-distance travel. Long-distance travel is usually done by driving or riding on a train or in a plane. The amount of carbon dioxide that planes produce each mile they fly is about 244 pounds. If an average plane carries 218 passengers, then the amount of carbon dioxide per passenger per mile is about 1 pound, or 2.2 kilograms. Long-distance trains, on the other hand, are slightly lower, emitting 0.19 kilograms of carbon per passenger per mile. An alternative energy and time-efficient method of transportation is needed to cut down these CO2 emissions. The MagLev system provides an alternative to both of these problems. MagLev provides an emissionless and reduced travel time solution to modern transportation. The modern train is very efficient for many people up and down the East Coast in particular. However, if the train could be redeveloped, it could become the premier way to travel long distance. This is the MagLev train. A MagLev train is a highly efficient train that can reach speeds of 200 to 300 miles per hour. This type of train doesn't have wheels and runs on a track. It is levitated by magnets in all directions. As opposed to a linear motor in regular trains, the MagLev train fully relies on north and south poles of magnetics throughout the whole track to keep the train moving.
Normal magnetics are not strong enough to fully levitate a train, so the most efficient way to produce this magnetic field is superconductors. Electromagnetic magnets are more powerful than permanent magnets because they are made of superconducting wires which can carry more electric current without melting. A ceramic superconductor is a material that conducts electricity with no resistance. For efficiency reasons, superconductor coils are placed on the track and on the trains, creating a strong magnet field 100,000 times stronger than the magnetic field of the Earth. Ceramic superconductors have a very high critical temperature. This means that they can conduct at higher temperatures than a metallic superconductor. However, these temperatures are still low for metallic superconductors and high for ceramic superconductors. As you can see from the graph, critical temperature of superconducting materials has increased over the years. Prior to the 1960s, the majority of superconductors were metal alloys that had critical temperatures below 23 Kelvin. Since then, oxide-based ceramic superconductors have been found to have increasingly high critical temperatures as high as 135 Kelvin. Properties and applications. There are different properties and applications of ceramics. Structurally, most superconductors have a tetragonal unit cell. This is the unit cell of yttrium barium copper oxide, which was the first superconductor found. Has side A equal to side B, but not equal to side C. However, the angles are all 90 degrees. In addition to the unit cell, the microstructure of ceramics have small grains. This leaves little room for slipping to occur, meaning that they are very strong and stiff. Processing. One way that wires are produced from brittle ceramics is the process known as powder and tube. Through this process, electrical conductors are made from brittle superconducting materials. Because superconductors reach such high temperatures, their material is too brittle for the normal wire process known as wire drawing, which is the process used to reduce wire cross-sections by pulling them through single drawing dies. The powder and tube method uses metal tubes which react to powders they are mixed with. Once they react, they flatten to form tape-like conductors, which result in the wires. The wires are not as flexible as normal wires, but can still be used.
In November 2004, the first operational maglev track opened in Shanghai, China. Through the mutual effort of German and Chinese engineering, the Shanghai maglev has demonstrated how magnetic levitation can move people in a way that is fast, reliable, and cost-effective. Though expensive to build, maglev trains have immense social and economic benefits. Studies by the Shanghai Maglev Transportation Development Company have shown the arrival and departure times of the maglev trains are on time 99.7% of the time. Commuting to work would get a lot easier when you could be 99% sure that the train you are riding was going to be on time to the station. Not only is the Shanghai maglev on time, but it is also incredibly fast, reaching speeds up to 430 km per hour, all while carrying 464 passengers. The Shanghai maglev cuts a regular 45-minute commute along a 6-lane highway to 8 minutes. The maglev route is economically friendly as well. It is elevated and does not interfere with other traffic, providing a high degree of safety. Wu Xiangming, the president of the Shanghai Maglev Development Company, describes the maglev as not only being safe, but also as a low-maintenance way of quickly moving passengers across vast distances in comfort. The commute is also much more comfortable. It is smooth enough that passengers can easily walk along the aisles without bracing themselves. In 1998, U.S. Congress established the maglev deployment program with the Transportation Equity Act for the 21st century. Today, there are plans for a Northeast maglev train connecting Washington, D.C. and New York. Compared to the high-speed Amtrak line already in place, the proposed maglev line would have 4 fewer stops and move 175 miles per hour faster. As previously stated, the main problem with implementing maglev trains is the economic costs. It costs around $200 million per mile of construction. This is proof that although maglev technology would be useful, the cost alone would not be feasible for areas that are unable to afford it.